For page 2, we're transitioning over to L'Hopital's rule, so we have a few problems to tackle here. We want to check to first make sure that we have an indeterminate form. So we have cosine of pi, which is -1, plus the sine of 2 pi. The sine of any multiple of or integer of pi will be 0, and then plus 1, so we can see that the numerator will go to 0. And obviously in the denominator, if x is replaced by pi, we have pi squared minus pi squared, which is also 0. So L'Hopital's is in effect. So here we go. The limit as x approaches pi, and the derivative of cosine of x is the opposite of the sine of x. And then we have chain rule in play for the sine of 2x, so that will be plus 2 cosine 2x. The derivative of the outer function sine is cosine with respect to the inner. That's why we have the cosine of 2x. And then we multiply by the derivative of the inner function, and the derivative of 2x is 2. The plus 1 will derive to 0. In the denominator, x squared will derive to 2x. Pi squared is a constant, and therefore it will derive to 0 just as the 1 did. So here is f prime over g prime. So now we will plug pi in again, and this time we get the opposite of the sine of pi plus 2 times the cosine of 2 pi. Sorry for the messy writing here because of the paper. And in the denominator we have a 2 pi as well. Okay, so the sine of pi, again, the sine of any integer multiple of pi will be 0. So we end up having 0 plus the cosine of 2 pi is 1, and we're going to double it, so it's 0 plus 2 over 2 pi, and therefore we have 2 over 2 pi, which will simplify to 1 over pi, so the answer is B. For number 5, if we plug 1 into the numerator, we get 0. If we plug 1 into the denominator, the natural log of 1 is 0, so we can L'Hopital's, so the limit as x approaches 1. In the numerator, this just derives to 1. In the denominator, the derivative of the natural log of x is 1 over x. So this becomes 1 over 1 if you prefer, but there's all 1s here, so that's going to be 1. And the answer again is B. For number 6, we have the limit as x approaches 0 of e to the x minus 1 over x. Obviously, the denominator is 0. In the numerator, we have e to the 0, which is 1, so we end up having 1 minus 1, so that's 0 as well. So again, L'Hopital's is in play. And yeah, you know, these problems all look like they're going to involve L'Hopital's, and they likely will, but you do always want to check because you never know what may happen. Okay, derivative of e to the x is e to the x. Minus 1 derives to 0. The derivative of x in the denominator is 1. So this is e to the 0 over 1, or just e to the 0, and anything to the 0 power is 1. So our answer this time is C. And last but not least, we have this following setup. This is a L'Hopital's problem as well. It's just a little presented a little differently. Let f be the function defined by 2x plus 3e to the negative 5x. And let g be a differentiable function with the derivative given by g prime of x is equal to 1 over x plus 4 times the cosine of the quantity 5 over x. It's known that the limit as x approaches infinity of g of x is equal to infinity. What's the value of this expression right here? Okay, so we want to basically plug in a very large value into g, and we see that when we do that we get infinity. So we have infinity in the denominator. And when we plug infinity, if we could, into the numerator, we have 2 times infinity plus 3 times e to the negative infinity. E to the negative infinity is 0, so this whole term would go to 0, but we have twice infinity there. So we end up having infinity in the numerator and infinity in the denominator. That is an indeterminate form, which means that L'Hopital's comes into play. So the limit as x approaches infinity of f of x over g of x will be equal to the limit as x approaches infinity of f prime of x over g prime of x. Okay, what we're told what g prime of x is, it is 1 over x plus 4 times the cosine of 5 over x. We need f prime. Well, f is up here, so we need f prime. The derivative of 2x is 2. And then we have plus, and then we have 3 times e to an inner function. So this is going to be a chain rule here. 3 is a coefficient, so it will stay, or move to our derivative rather. And then we have e to the negative 5x. So that's e to an inner function. The outer function is e, the inner function is negative 5x. So we derive the outer, and e derives to itself with respect to the inner, so e to the negative 5x. And then we must take the derivative of the inner function, and the derivative of negative 5x is negative 5. So putting this 3 and that negative 5 together, we end up having 2 minus 15 e to the negative 5x. All right, so what happens here? Well, whoops, I left out my limit. Shame, shame. Limit as x approaches infinity. Okay, so if we plug in a really, really large number, there's no x here, so we just get 2. And then we have minus 15, and then we have e to the negative infinity, which I'm just going to write in like that for now. And then down below, we have 1 over a very large number plus 4 times the cosine of 5 over a very large number. Okay, so what's happening here? Well, 5 divided by a very large number is 0. So we really have the cosine of 0 here. 1 divided by a very large number is also 0. So what we really have in the denominator is 0 plus 4 times the cosine of 0. Cosine of 0 is 1, so we really have 0 plus 4 times 1, or 4. That's our denominator. In the numerator, we have 2 minus 15e to the negative infinity. Right? So as x gets really, really close to negative infinity, e, remember our graph, gets really, really close to the x-axis. In other words, this whole term will go to 0. So we end up having 2 minus 0 in the numerator, and that's why the answer is B, 1/2.